Hi, welcome to the solutions to problem 15 of the post-midterm review. In this problem, we're not given the matrix X, but rather the singular value decomposition and the matrices for it, U, sigma, and V. So for the first problem, how many rows and columns does X have? What is the rank of X? Recall from the definition of singular value decomposition that the dimensions of U are n by n, for sigma it's n by d, and for V it's d by d. So to find the dimensions of X, we simply have to look at the dimensions of sigma, which is 2 by 3. As for the rank, we want to look at sigma again, but in a slightly different way. First, we'll start by going back to how the matrix is defined. Sigma contains the square roots of the eigenvalues of X transpose X, and by extension, XX transpose, because both of these matrices have the same eigenvalues. They also have the same rank, though. A property that they happen to share with the original matrix X. Recall that for eigenvalues, the only way a matrix can have a non-zero eigenvalue, or rather, the only way a matrix can have a zero of eigenvalue is if it's not full rank. And the values on the diagonal of sigma have to be greater than 0. This means that the matrix XX transpose has to be full rank, and since XX transpose is a 2 by 2 matrix, it's going to have to be a rank of 2. In other words, the rank of X is also going to be 2. For the second part, we have to find V2, and to do this, we're going to use the properties of V being an orthogonal matrix. If we take a look at V, we'll notice that the first column has both of the same value in the first and last components with a 0 in between them. This means that we can pretty easily get them to cancel out by say dot producting them with a vector that's 1, 0, minus 1. But this is an orthogonal vector, but it's not going to give us an orthonormal set, which is what we're looking for the matrix V. To do that, we have to make this a unit vector. We can accomplish that by scaling it down by its length. In other words, the length of this vector is the square root of 2. So we would divide this vector by square root of 2 to get 1 over root 2, 0, and negative 1 over root 2. And that's how we find a V2. Note that negative 1 over root 2, 0, and 1 over root 2 would also work here. Like either one of those vectors is acceptable for this. For the last part, given that the first column of X and the third column of X sum to the vector 0, 5, find sigma 1. We'll ignore the part given in the beginning of the problem statement first and focus more on the hint, though, which is that when X is multiplied by a right singular vector or a column of V, that is equivalent to a left singular vector or a column of U being scaled by their corresponding singular value, sigma I. So how are we going to apply that in practice for this problem? We can start by setting up the equation. Since we're looking for sigma 1 here, we're going to use I equals 1. So that means X times V1, or X times the first column of V, is going to be equal to sigma 1 scaling the first column of U. If we plug in our vectors, it would look something like this. So, what's left to do here? Well, recall that when you multiply a matrix by a vector, you would interpret it as taking a linear combination of the columns of your matrix by using the components of the vector as weights. Since there's a 0 as the second component and non-zero values as the first and third components, we're effectively scaling the first and third columns of X and adding them together, and we're ignoring the second column. So we would get something like this, where x1 and x3 are the first and third column vectors of x. Now we can finally use what's given to us in the beginning of the problem, which is that the first and third columns of x sum to the vector 0, 5. We can factor out the 1 over root 2 to isolate x1 plus x3, which we can then plug in the vector 0, 5 for. All we have to do from now is to just apply the scalars directly to the vector, and we'll see exactly what the value of sigma is. And that's the solution to problem 15. Hope this helps.